Good morning, everybody in Chemistry Land. Today we're going to start with Chapter 15 on our first podcast of this chapter. And we may have already talked a little bit about solutions in class and seen some demonstrations. And now we're just going to make sure that you have all the information straight. And again, as we probably talked about, that solutions are something that you probably do have in your hand every single day in terms of the beverages that you're drinking or things that we're eating or the air that we're breathing, all these different things. So if we take a look at forming solutions, what is a solution? You always have to remember, and when we start looking at these calculations, you cannot lose sight of that every solution has to have two parts. And the two parts are the solvent and the solute. Keep in mind that we said that a homogeneous mixture is a solution, and remember that a homogeneous mixture has to be very uniform. And when you are taking a drink of your favorite soda or whatever it is, you as a consumer expect to be the first sip the same as the last sip. If not, you may not buy that product again. And so a solution needs to be a homogeneous mixture. And if you take a look at the two different parts, you can see they are right here. We have our sugar, which is going to be our solute, the substance being dissolved. And then we have our water. And our water is going to be our solvent, the substance doing the dissolving. And then once they get dissolved, you can see over here we have our homogeneous mixture. Homogeneous mixture, that this is a physical change. And so we would be able to boil this back. If we boiled this back and all the water escaped, we would be left behind with some clumps of sugar on the bottom. And so this is indeed a physical mixture. Many of our solutions are aqueous, meaning that a solution with water as a solvent, when we were writing our balanced equations, we wrote AQ. And what that means is that we had a solute dissolved into a solvent. Now, we always think of solutions, or we often think of solutions as liquids. And there are all kinds of solutions out there that aren't always in the liquid state. So this is exactly from your book, state of the solution. So this is how we see it, okay? So our air or natural gas is going to be, it's in the gaseous phase. You really have a gas dissolved in a gas. Antifreeze, you probably have some of that in your vehicle, and your state of solution is a liquid. This is more what we usually see, but often we see a solid dissolved into a liquid. For antifreeze, you have a liquid dissolved into a liquid. Brass, we have brass all over the place. It's solid, you can see it, but how it was actually made was a solid dissolved into a solid. Carbonated water, you can see that as a gas into a liquid. We probably talked about that in class. And seawater is a sugar solution. So we have all these different forms. They don't always have to be a solid dissolved into a liquid, but for purposes in class, that's the easiest way for us to show it and for you to view it. So here it is again. We have a solid, we have NaCl dissolving in some water, and we get our solution of salt water. So what does it really mean to dissolve? What has to happen to here? Does this magically disappear, or does this magically just take it all in? I don't really think so. We like to see magic, but science is not based upon that. So there's a certain process. If you think about this, remember, I'll always be the water molecule. We're talking about that all the time in class. I have to create some space. Just like if you and your friends are sitting on a bench and someone else comes along, I would hope that you would scoot on over and make some space for your friend to sit down with you. The same thing has to happen here. For this NaCl to be able to dissolve in here, there has to be space. If there isn't any space left, then I'm not going to be able to dissolve any more salt into my solution. So what is that solvation process? It's the process of a solute dissolving in a solvent. Now, we have talked about in the last chapter how ends are going to be charged. And we know that with water, the hydrogen end is going to be slightly positive and the oxygen end is slightly negative. So as I take a look and apply this to both of these, this cation, which we know is positive, a positive cation, and then we have an anion, which makes our ionic substance, that the water molecule is going to attack this. There's going to be collisions here, but the collisions are going to happen in a certain direction, as you see here in this picture. The direction of the water molecules, you can see I have my sulfur closest to this right here. Well, my oxygen side is negative, all right? Well then, if this is the negative side, what does this have to be? We know that opposite charges attract, has to be my positive cation of sodium. Down below here, we know that hydrogen is slightly positive, and so if all these positive hydrogen are around this substance, then this has to be negative, which ends up being our negative anion. These collisions will continue to occur until we break apart all of this ionic substance. It's continuing to create space, and when that stops, we will not have any more dissolving happening. Now, in order for things to dissolve, they have to be of like situations. Polar dissolves polar, nonpolar dissolves nonpolar. Well, if we take a look at some of these substances, you can see that when it has an OH right here, all right, this is ethanol, rubbing alcohol, that this is going to attract to the side of water. So it is going to be able to break apart. Now, if we take a look at glucose or sugar, you can see on here that even though I have a non-ionic substance, is what they call it, meaning I don't have a metal transferring electrons to another non-metal, I actually have some sharing of electrons, so I have a covalent structure here, but I have lots of hydroxides. Whenever I have lots of hydroxides, it's going to be able to dissolve. So why is solid sugar soluble in water? Well, we have to first understand that it's non-ionic. And remember that an ionic substance is a metal to a non-metal. I look all over here in my structure up here, I don't see any metals. So we call it non-ionic. But it has many OH groups. These are alcohol or hydroxide functional groups, and which shows that it's an alcohol. It can be an alcohol, but in this case it isn't. So this is a hydroxide functional group. It has many of these, and they are attracted to water. Because you have that attraction, then you're going to be able to dissolve in water. Because this has a difference in charge, this also does too, so those positive and negative charges are going to attract. Now, if I take another situation where we know that oil and water, they do not dissolve in each other. So substances insoluble in water means that they don't dissolve. Well, you guys have experienced this in our classroom, you've experienced it in your kitchen, you know that they don't dissolve. Well, if I take a look at my structure, I don't see any OHs in here. I don't see any difference in charges, and so there's nothing for the water to be attracted to. So if you take a look at the two of the points here on the right, nonpolar oil does not interact with polar water. So this is oil is going to be nonpolar, this is going to be polar. That is not going to attract to each other. There's no excess of charge here. Water hydrogen bonds keep water from mixing with the nonpolar molecules. They're attracted to each other, but they're not going to be attracted to that oil. And so, again, we have the situation where like dissolves like. You're going to see that again in just a second. So in the three-step process of how we're going to dissolve things, the solute particles must separate from each other. So we have NaCl. This is my solute. Well, if I am going to separate them, I would separate this into its positive ions, its negative anions, so they are going to separate. Then the solvent particles must separate to make room for the solute. Like I just talked about, the solvent particle, if this was you sitting on a bench, you would have to make room for that solute to get in there. The interactions have to happen. Like oil and water, there's not going to be any interactions, but NaCl and water does. So there has to be interactions. There has to be attraction between the solute and the solvent. So we go back to the phrase that I've been mentioning all along, that like dissolves like. So it is going to be polar is going to dissolve polar substances, nonpolar is going to dissolve nonpolar substances, and then what do we do with our ionic substances? Polar molecules, because ionic substances are charged, can also dissolve anything that is ionic. Remember, ionic is NaCl, a metal to a non-metal. All right, so that's what I wanted to talk about here. And the next part with solution composition, you probably have already heard this in class. I showed you some different examples of a saturated solution, an unsaturated solution, and showed you this slide already. And then we did our best at looking at a saturated, a supersaturated solution, which is very rare. And we talked about solubility curves. All right, well, I hope you guys are having a wonderful day, and I will see you soon in class.